So in order to deal with the interaction between chemical systems and electrical systems, we need to start with redox reactions, because that's really the heart of what's going on. So remember oxidation-reduction reactions? This is way back in week 2 or so, week 3 maybe. So reactions where electrons are transferred from one atom to another are called oxidation-reduction reactions, redox reactions for short. Atoms that lose electrons are being oxidized. Remember this, oil, oxidation is loss of electrons. Atoms that gain electrons are being reduced. Reduction is gain. So if some atoms are losing electrons and other atoms are gaining electrons, then the electrons are moving. And that electron motion is the key. So as just a reminder, increase in oxidation state is oxidation, and decrease in oxidation state is reduction. Remember, we learned how to assign oxidation states, so we could see which species, and particularly which atoms were deficient or had a deficiency of electrons or a surplus of electrons. A simple redox reaction, if we have sodium metal and a chlorine gas that can react to produce sodium chloride, where we've actually put the ions, charges in to be clear what's happening. So sodium to a sodium ion, plus 1 electron, the sodium is being oxidized to the sodium ion. And so in other words, sodium is going from a 0 oxidation state to a +1 oxidation state. It is a slight deficiency of electrons, whereas chlorine in chlorine gas, +2 electrons goes to 2 chloride ions. And so the chlorine is going from the 0 to the -1 oxidation state. It has a slight surplus of electrons. But this particular reaction is favorable because even though sodium might have a few less electrons than it might like, and chlorine might have a few more than it initially has in the chlorine gas states, it reaches a more stable state if it can, if that electron can switch places. It becomes lower in free energy. Okay, so when we talk about electrical reactions, we talk about them in terms, it's easiest to think about them in terms of half reactions. We split the redox reaction into 2 separate half reactions. Each of them are reactions that involve just oxidation or reduction, but not both of them. So the oxidation half reaction has electrons as products, right? Oxidation is loss. So you're going to get electrons being produced. The reduction half reaction has electrons as reactants, right? The electrons are gained in reduction, so therefore you have to add electrons as a reactant for that to happen. Here, for example, we've got chlorine plus iodide plus 3 H2O, and we get a redox reaction where we get 6 chloride ions plus iodate ion plus 6 hydrogens. And in this case, the chlorine starts at 0, and then it goes to a -1. The iodide goes from -1 all the way to +5. And the water and the oxygen actually don't change oxidation state, but changing the molecules they're part of is necessary to create the stable final reactants with the oxidation states they have. So in this case, the oxidation step, and here we're just looking at, we're not including the oxygens, we're just looking at the actual parts of it that involve change, the atoms, molecules that have atoms with changing oxidation state. The oxidation, iodide going to iodate plus 6 electrons, right? Because it's going from a -1 to a +5 oxidation state. It's increasing in oxidation state by 5, which means it had to give off electrons for that. Oxidation is loss. The iodine atom loses 6 electrons as part of the process of creating an ion with 3 oxygens. And the reduction is same one we saw on the previous page, chlorine gas plus 2 electrons going to 2 chloride ions. And so that we can multiply the second one by 3. Oops, there's actually a typo there. Let's fix that. 3 there. Okay, now it's balanced. Yeah, so we take apart the reaction into half reactions, and it's a little easier to deal with them as half reactions. Okay, so frequently what we have to do in these situations is balance redox reactions, and we're going to do this by the half reaction method. The reason we have a sort of a special way for balancing redox reactions in solution is that in solution frequently the parts of the reaction react with water as well, and so you get these side reactions with water, so you can't necessarily assume that the reaction just involves the things you put into the water. It could involve the water as well. So we have a procedure that helps us deal with that. So it's a helpful way to balance complex redox reactions in solution. Break it down into two half reactions, one for oxidation, one for reduction. And then each half reaction is balanced individually for both atoms as charges. And you explicitly put electrons in as carriers of charge. And then you add the two half reactions back together to get the overall balanced equation. So in solution, this is the key. So you write out the compounds with changing oxidation number as two half reactions in the net ionic equation, and balance all the other atoms. And if you frequently, this can be done by inspection because usually there's not many species involved. You could use the algebraic method here if there happens to be several different species that are moving atoms back and forth. And then you balance the oxygens by adding H2O, because H2O frequently does start reacting in these situations. Balance the H's by adding H plus for either acid or base. And we'll get to why you would do this in a basic solution as well. Add electrons to balance the charge. And if you've done everything right up to here, then you've essentially balanced the charge except for the electrons. So you add electrons to balance the charge, and you'll get the oxidation, the same electrons you get from all of the different oxidation reactions occurring. And then you add together the half reactions to cancel out the electrons from both reactions, because electrons should not appear in the final equation, just in the half reactions. And you might need to multiply one of the half reactions by some factor in order to get them to cancel out. Okay, and if an acid, you're done. You've got a reaction that explicitly has hydrogen on one side and none on the other. If in basic solution, then you simply add OH minus to neutralize the H plus on both sides, and you get how that reaction would behave in a basic solution. And then you just check, as usual, by counting atoms to make sure those are balanced and make sure the total charge is balanced. A chemical reaction should not have a change in the total charge. That is not possible for a large number of species reacting, because you get a buildup of charge, which would be highly, highly, highly unfavorable. So any feasible reaction must have balanced total charge. So one question is, why not the algebra method? As I hinted at before, we can add as many H2Os and H pluses or OH minuses as needed. And that's a lot harder to handle by the algebraic method if you don't actually know all the species that are there.